Okay, I'm hitting record here. Great. Okay, now before you guys were born, I was teaching work energy power to Camps Bay High School, and this is sort of how we teach work energy power. We teach it by saying that work is force times distance. Okay, so work is force times distance. So what did I do at Camps Bay High? I said to them, let's see how much work you guys can do. So here is, I'm going to show you. I would normally get, like we got the kids at Camps Bay to do this. I'm going to show you what we do. Work is force times distance. So here's the formula. Where is it? Work is force times displacement. I don't think you can see it on the board. Work is force times displacement. So then we got the kids to do this, and I just want to show you. We stand on a bench. We go 1, 2, 3, 4, 5, 6, 7. Okay, I did that in 10 seconds. Could you guys see me? Did you guys see me? I'm not doing it again. So that's what they were doing. So now you've got to work out how much work did I do. So we take work equals force times distance. So if you can see my blackboard, work equals force times delta X. What is my force? Well, force equals mass times acceleration. So how much work did I do? Work equals mg, and delta X is h. So what is my mass? I'm 100 kilograms on a good day. What is g? 9,8. And what's the height that I did, that I climbed up onto? 0.5 meter. This bench is 0.5 meter. And how many times did I do it? I think I counted 7. So it's 100 times 10 is 1,000, divided by a half is 500 times 7. You could work it out. You guys just want to work out how much work I did. Okay, it's 100 times 9.8 times 0.5 times 7. I did 3,430. Joules of work. All happy? Hands up if that makes sense to you. Won't you just put a hand up if it made sense to you? Okay, thank you. So work is actually equal to force, which is my mass times gravity, times distance, which is the vertical height, and how many times I did the vertical height, and there I did 3,430 joules. And then what we got the kids to do as well was to do press-ups. I just want to get this off. So how do you do a press-up? You get a bathroom scale and you switch it on. And then you do a press-up. 1, 2, and you see how many press-ups you can do in 10 seconds. And then you work out your work, how much you did. Everyone cool with that? Happy?
Yes.
And another way you could do it is we got some kids to hang from the door frame, and they were doing chin-ups. So again, it was their mass times g times how much height they were pulling up. So before you were born, back in 2002, we were busy doing this practical. Some kids were on the desk jumping up and down. Some kids were hanging from the door frame. Some kids were doing press-ups. And the principal, who was Anne Line at the time, walked past and said, "What is going on here?" She couldn't see any teacher because I was arm wrestling with some person, and I was surrounded by this whole group of kids. And so we were trying to figure out who was the most powerful person in the class, or who did the most work in the shortest length of time. Okay, so this is what I would recommend you guys go and do at home. Go and climb on a chair, time yourself for 10 seconds. How many times can you jump onto that chair, stand straight, and so on? And then see what your work is that you can do. How much work can you do in 10 seconds? Okay, so there's homework for you. Or you could do press-ups, but then you need a bathroom scale to press up on a scale, because on a scale, the upper part of my body is the only weight, and that weighs 60 kilograms. So I've got to use 60 instead of my whole body weight. So that's more complicated. Let's get this out of the way. Another way you can do it is you can run upstairs, and then you measure the height of the stairs, and then you go mg and the height of the stairs. Your weight times the height of the stairs will give you how much work you did, or how far you can run in 10 seconds. Okay, so that is work. It is a force times displacement. We don't use distance, it's force times displacement. Okay, now let's go to the formula. Is force a vector or a scalar? Who says it's a vector? Hands up. Force. Okay, well done, you guys. So we can put a little arrow. Who says that displacement is a vector? Displacement, not distance, displacement. Is that a vector? Grade 10? Hands up, who says it's a vector? Can I put an arrow above it? Yes. Okay, so force times displacement, two vectors equal, who remembers? Two vectors equal a vector or a scalar? Who says two vectors multiplied together gives a vector? Is work a vector or a scalar? Who says work is a vector? Who says work is a scalar? Matsadiso is correct, and one or two others. Well done. So work is not a vector. So what is the rule? -1 times -1 equals +1, if you want to think of vectors as -1. So vector times vector is a scalar. Okay, so does your answer, this, have a negative or positive? Does the work ever have a negative or positive? Who says it can have a negative if it's a scalar? I see hands going up there. Now, you see, this is where it gets a little difficult. Scalar quantities, they can be negative. I guess you can have a negative scalar quantity, but they don't normally have a direction. Okay, so normally the negative means the direction. Okay. So, but just keep in mind, work is measured in joules, and joules is a scalar. It's not supposed to have a direction. Okay, now, what is power? Okay, here's the formula. Power is work divided by time. So let's see how powerful I was to stand up this many times in 10 seconds. So let's go to my blackboard. Power equals work divided by time. And how much work did I do? I did 3,430 joules in 10 seconds. So my power is 343 watts. Okay, do you see that? Power is work, which was 3,430 divided by time, which was measured in seconds. If we divide this number by 10, I just move my decimal comma and I get 343 watts. Okay, so that's how powerful I am. I am the equivalent of a fairly bright light bulb. I'm not very powerful. Okay. If you compare me with like these Olympic people, they can lift huge weights in a very short period of time and they would be very powerful. Or like a Tour de France cyclist, they can get the power really going. Okay, but I'm not an athlete, I'm just a teacher. Does everyone understand how you get power? Divide your work by your time. Okay, so when you have stood on your chair 10 times, I mean, not 10 times, as many times as you can in 10 seconds, measure the height of your chair. Your chair is not necessarily half a meter. Take your weight, which is your mass times 9.8, times the height of the chair, times how many times you do it, and then divide it by 10 seconds, and then you'll get your power. And let's see if any of you are more powerful than me, 343 watts. But let me tell you what normally happens. You're all lighter than me. Heavy people are powerful. It's just a fact. And that's why heavy people don't compete in the Olympic Games against little, thin, small people because they're less powerful. Okay. So us big chaps just tend to have more power because we're used to carrying so much weight around. So that makes us strong. That's the positive side of that. I'm just going to spin that. Okay, so now you know what work is and power. We have to look at some other formulae. Okay, hands up who's heard of potential energy? Who's heard of potential energy? Matsadiso and quite a few others. Okay, and you know the formula for potential energy? EP equals mgh. And another thing we could call it is capital letter U. Okay, so potential energy is mass mgh. It's almost like what I did here, work, mgh. I increased my potential energy every time I stood up on the chair. So it's the same thing. Okay, who's heard of kinetic energy? Okay, anyone not heard of kinetic energy? Hands up. And that is the formula. There we will see it. Half mass times velocity squared. Okay. Now here is something new, or maybe I taught it, so I can't remember. Last term was a long time ago. But the sum of your kinetic and potential energy is known as, anyone know? Hands up. The sum of potential and kinetic energy is given the name, anyone know? It's called mechanical energy. Mechanical energy. Yeah, they don't really have a formula that I can see here. That is the closest you get to it. Your change of kinetic and change of potential, if you add the two up together, you get your change of mechanical energy. And your change of mechanical energy is equal to friction. Okay, so now the next thing, if I was telling teachers how to teach, the next thing we would do is, let me just share the screen with you and see what happens. I'm looking for preview. Okay. So let's just go to your paper 1 booklets. I would go to the formulae and get you to, let's just find the formulae. Okay, it's on page 5. You guys all see that? Are you seeing what I'm seeing on this page now? You seeing this page that I'm showing you with the formulae? Hands up, just thumbs up if you see it. Okay, fantastic. Okay, You know that your textbook is rubbish on work, energy, and power. Sorry, study and master, you're fantastic in many regards, but honestly, I went through it yesterday to mark it, and it's pretty rubbish. This is actually a better summary. Okay, let's just read it here. Work is work done by a constant force is defined as a scalar quantity. It is equal to the product of the force multiplied by the displacement. Force times displacement. And then it's got some other stuff here. Now, do you know that in the old days, we never had a cos theta? Now they've added since 2013 when CAP started, they added this little thing to the formula, cos theta. So it's force times distance times cos theta. Okay. You can rewatch this video, but let me tell you what cos theta means. If you are moving in a certain direction, let's say you're moving down, and there's a frictional force in the opposite direction, cos theta is the difference between the force and the direction that you're moving. So if you've got force is moving in the same direction as you're moving, then theta is 0. But say you've got frictional force, then friction is at 180. So now you're going to get cos 180. And that cos 180, if you type it into your calculator, gives you -1. So what it's saying is, if your force and your displacement are in opposite directions, your work must be negative work, which sounds almost like a vector quantity. I'll say that again. Since they started CAPS, they added cos theta. Cos theta is the angle between the direction you're moving and the force. So suppose I'm moving to the right and there's a frictional force to the left, then the angle between me moving to the right and the frictional force is 180 degrees. So now you're going to write frictional force, or force times distance times cos theta is the angle between the direction you're moving and the force direction. And frictional force is always at 180 degrees, therefore it's -1. Cos 180 is -1. But you could get a force that's pulling in the same direction. For example, you could get a string pulling something on a desk, and that's pulling in the same direction as it's moving. And then what would your theta be? Who says your theta, if you've got a string pulling a weight, you've got a force in the same direction the weight is moving, who says theta will be 0? Hands up. Who says theta will be 0? Yeah. And cos of naught is +1. So then you can kind of ignore it. So it's to give you a sign to your work. Okay, then let's have a look at kinetic energy. Is the energy an object has due to its motion? There's your famous formula. EK equals 1/2 mv squared. And guys, on your data sheet, you could also just use the letter K. And that is the same as EK. So you've got a choice. Whichever you want to use, you can use K or EK. Now let's have a look at this. Gravitational potential energy is the energy an object has due to its position in a gravitational field relative to some reference point. Woo! Okay. A simple definition is gravitational potential energy is energy which an object has by virtue of its position. Boom. Could stop there. And then it's equal to mgh. Now here's mechanical energy. This is what I was talking about. Total mechanical energy is equal to the sum of the gravitational potential energy plus the kinetic energy. So EM equals EK plus EP. This is not on your data sheet. Okay, so that formula is just like common sense. Add your kinetic and potential energy, and then you've got it. Okay, then power, we've just had a look at. Power is the rate at which work is done, or work done over time. Thanks, Aiden.
Oh, he's just illustrating.
Okay, so power is work done over time. And now we come to something here. Called the work, energy, and the principle of conservation of energy. The work done by the resultant net force acting on an object is equal to the change in the kinetic energy of the object, or work net equals delta EK. Work net equals delta EK. They messed up this kind of, the narrow column, just that there, and that is called the work energy theorem. Okay, work net equals change of kinetic energy. Okay, so let me ask you a few quick questions. If something gets slower, has it changed its work net? If work net is equal to the change of kinetic energy. If the kinetic energy changes, has its work net changed? Yes or no? Who says yes? If you change kinetic energy, do you change work net? Yes. Okay. So I'm going to ask that question again. If you change kinetic energy according to the work energy theorem, your net work is equal to change of kinetic energy. So whenever something speeds up or slows down, you're going to get net work done on it or done to it. So if something speeds up, has it got a change of net work? Who says yes? Yes, hands must go up. If something slows down, has its network changed? Yes. If something stays at a constant velocity, has its network changed? No. Okay. So there, that's how you recognize when you must use your work energy theorem. Whenever something's speed is changing, net work has done to it. Because look, do objects change their velocity without some energy being put into it? Let's say there's something on your desk. I can see there's something on the desk, lying on the desk. If that thing had to just start moving, meaning change its kinetic energy, and no one gave it energy, I would think a ghost had moved it. Then I'd say we're dealing with a paranormal, not science, right? But you know that if something has to start moving, you've got to give it energy. Or if you've got to stop something, you've got to take energy away from it. Okay, so you guys kind of know that. And then total mechanical energy in an isolated, so here's the law of conservation of mechanical energy. Total mechanical energy in an isolated system remains constant or is conserved. And you know what? I meant to go to a whole lot of trouble and make you a pendulum, but I forgot to. So I'll just have to swing my glasses like this. If it was on a string, we'd have a pendulum. And this is how a pendulum works. Okay. So we'll just have to, I was going to get a nut. So here's the thing. It swings like this, back and forward, back and forward. Now what they're saying is, when your pendulum is there, it's got a certain amount of energy. That's, we normally say it's got potential energy, but it's standing still, it's got no kinetic. Then when it gets to the bottom, it's got no potential energy, it's all become kinetic energy. And then when it swings back there, it stops. So it's got no more kinetic energy, it's just got potential energy. So energy is conserved, but it's changing all the time. Potential to kinetic to potential, back to kinetic to potential. All happy with that? So the energy is conserved by the law of conservation of mechanical energy. So we can give you a different situation, which is the one that normally comes in the exam. I'm just looking for my eraser. Okay, well, here's another situation. Here we've got a skier on a slope. Okay. And then at the bottom of the slope, there's the skier. Here's position A, here's position B. Okay, now at A, or the top of the slope, what type of energy has the skier got? Who says the skier's got potential energy? Hands up. Who says it's got potential energy? Has it got potential energy? By virtue of its position? Hands up. There we go, it's got potential energy. Because it's got a height, it's like potentially there. Okay, now it slides, he slides or she slides down the slope. Let's make it her. She's sliding down the slope. Now she's got no more height, but she's got what type of energy? Who says she's got potential energy at the bottom? Who says she's got kinetic energy at the bottom? Hands up. Has she got kinetic energy at the bottom? Matsutiso, what do you say? Kinetic energy at the bottom? Yes or no? Okay, so now she's moving at the bottom, right? So she's got kinetic energy, which is half mv squared. So let's suppose she had X amount of energy at the top. According to the law of mechanical energy, how much energy will she have at the bottom? Who says she will have more than X? Who says she will have X? Who says she'll have less than X? Okay, well, what is the answer? According to the law of conservation of mechanical energy, she's going to have the same amount of energy at the top and at the bottom. I just want to stop that and go back to stop share. Okay. I think you can see me now. Can you see the board a bit bigger? Is that okay? Now she's got kinetic energy. Now, the next thing that she can do is, she hasn't lost this thing of energy. This is frictionless. Now, let's suppose she comes to a bump. Who says that if the bump is a small bump, she can go over it? Hands up. Will she be able to, has she enough energy to go over a small bump? Yes. Who says yes? Who says no?
Yes.
Yes. Okay, yes. Okay. She can go over it. And if there's no friction, she can go over hundreds and hundreds of bumps. It doesn't matter at all what path she takes. Now she comes to a hill. So she gets to a hill that's higher than the original hill. Here's my question to you. How far up that next hill can she go? Who thinks they've got an answer? By the law of conservation of mechanical energy, if you've got no friction. Any thoughts? Shout it out, come to the front and give an answer if you want to. Just keep social distancing. But surely you must have some idea of the height that she can go up the next hill. Where is she going to stop on the last hill that's higher than her original hill? Any ideas whatsoever? Anyone got an idea? Just a hands up. Okay, who says she will end up lower than where she started? There's no friction, right? She's just on super fast ice. Who says she'll end up at the same height as she started? Well, you would be the genius that says that. And who says she can go higher than when she started? Nah, then you'd be getting something for nothing. You'd be getting something free. So we know that if she starts at Let's suppose this is a 10-meter hill. She can go anywhere she likes over every single little bump, but when she gets back to 10 meters, that is where she's going to come to a halt. At that exact point. Why? Law of conservation of mechanical energy. So was that super easy or super difficult? I found it very easy. But now you've just got to remember that. Okay. Now here is what you've got to, now the next thing you've got to know. We call force we call it conservative or conserved energy, as opposed to friction, which is an NC. This is a C, conserved energy. And here's the difference. Tell me, did I care what path the skier took? Will it always reach the same height? Who says it doesn't matter what the path the skier takes? Hands up. Come on, you got to say something. Yeah, okay, brilliant. And who says it does matter what path she takes? Okay, so those brilliant for not putting up hand. But you see, this all works until we introduce a thing called friction. Now, if this path had friction, would it matter what path we take? If it had friction? Who says it would matter? Hands up. Yeah. Why? Because the longer the path, the more the friction you're going to encounter, force times distance. So we call friction a non-conservative force. We call gravity a conservative force. Friction's an NC. So you will find that definition in your textbook, and they tend to ask it in the exams. Define a conservative force. It's a force where the path of the force does not matter. What is a conservative force? It's the path of the force does matter. Okay. So here we have a formula for work done by a non-conservative force. Okay, come on, guys. You've got to be awake here. You've got to make me look good. Okay. Whenever I talk about WNC, I always mean friction. Come on, remember that. You're only dealing with mechanical energy and friction. Mechanical energy, it's conserved. Friction, it's not conserved. Okay, so when I say WNC, I mean work done by a non-conservative force, meaning friction. And what is work non-conservative equal to? Change of kinetic and change of potential energy. In other words, those two add up to mechanical energy. So the thing that changes mechanical energy is friction. That's all that formula is saying. WNC is equal to a change of kinetic and potential together means, but is a change of your mechanical energy. Okay. Now here's a typical problem in the exam. Right, I hope you can see that. Here's would be a typical problem in the exam. Let's get you guys to do some work. I think you need to get some active. Let's give that girl some weight. Okay, she's petite. Let's give her a mass of 50 kilograms. Let's give G a G of 9,8. And we've already got a height of 10 meters per second. Okay. Do you mind? I think we lost the class there, but they'll come back. Okay, so Matsudiso, would you mind just working out how much potential energy the girl has got at the top of the hill? And you're going to use EP equals mgh. I think they got cut off or lost their signal on that side, but they'll rejoin. So their potential energy is mgh. Okay, so the mgh is 50 times 9.8 times 10. Did you get an answer, Matsudiso?
Yes, sir.
What did you get?
4,900 joules.
There we go. Okay, so energy is 4,900 joules at position A. Now, Matsudiso, what will her energy be if mechanical energy is conserved at position B?
I think it'll be more.
Will it be more or less?
I think it'll be more.
And how much more? What will it come from? Coming down the hill?
Yes,
you think
sir.
that's where it gets the energy from? Okay, but now listen to this. That's how much energy she has at the top of the hill. It's not that her energy gets more, it just changes to a different form, meaning it changes from potential energy to kinetic energy. Does that make sense? So she's still got 4,900 at the bottom, but it's now kinetic energy. That's what the law of conservation of mechanical energy is. It's the same as your pendulum swinging. It's not changing in energy, it's just changing from one form of energy to the next. Does that make sense to you? Does that make sense?
So the thing was hacking.
Sorry?
The thing was hacking.
Oh, could you not hear me properly?
No, sir.
Okay. Just let's see if you can hear it properly now. Okay, here again. At the top, she's got 4,900 joules of potential energy. At the bottom, you've got to remember she's got the same amount of energy, but it just changed to a different form, which is kinetic energy. Okay. Can you hear me okay now?
Yes, sir.
Okay, so she's still got 4,900. Now Matsudiso, she skis along to C on a frictionless surface. How much energy has she got at C? How much energy has she got?
Less.
It's frictionless.
I think she got less.
She's still got the same amount. It's still 4,900. Okay. And then she comes to a hill, and when she gets back to 10 meters on the top of the other side, you know how much energy she's got there? Still 4,900. Does that make sense?
Yes, sir.
So everywhere she goes, the energy is going to be 4,900. You can't lose energy. It's the law of conservation of energy. The energy cannot be created or destroyed. It can only be changed from one form to another. So here, what type of energy has she got again? At the top of the hill she's got?
Potential energy.
Potential mechanical energy, correct. At the bottom here, she's got
Kinetic energy.
kinetic mechanical energy. Here, she's still moving at the same speed she's still got.
Kinetic.
Kinetic mechanical energy. And when she gets back up top there, she's got
Kinetic mechanical energy.
well, she'll come to a stop at the top. So now
And
she's
it's
got
potential.
energy again. Does that make sense?
Yes, sir.
Okay. Now there's only one thing that can change that, the height that she goes. And that is if we introduce our friend friction. So let's introduce friction. Sorry. I'm just not sure if our class can see or hear, but I don't see them. It looks like they left the meeting. Okay, what type of road is this, Matsadiso? Is it a frictionless or a friction-full road?
Friction.
Okay, you can see it's got all these sharp edges and bumps. Now, the moment we introduce friction, Matsadiso, is she going to be able to get to the top of the hill?
No.
There you go. The moment you got friction, she's going to end up somewhere below where she started. Because friction is a non-conservative energy. It takes away from mechanical energy. Happy with that?
Yes, sir.
Okay. Now, I suppose we want to know how do we play around with this WNC? Okay. Matsadiso, let's suppose she comes to a halt at 6 meters above the bottom. 6 meters above the bottom. She comes to a halt. What happened to those last 4 meters worth of energy? Where did it go? If normally that amount, she would have that amount of energy normally. Where did it go? It went into friction.
The friction.
So Matsadiso, can you work out that if that is 6 meters, we know that she had enough energy for 6 meters. Can you work out M times G times 4 meters? And that would be how much friction, how much energy was lost due to friction. Okay, so just work this out, MGH, where M is, she hasn't changed her weight, she's still 50. G is still 9,8, but she's lost 4 meters of the hill. So just do that calculation. 50 times 9,8 times 4. 50 times 9.8 times 4. And that comes to 1,960. You know what, Matsadiso? You know what I think may have happened? I think what Zoom may have done is, if there's more than one person, they stop it after 45 minutes. So I'm going to just log off and re-log on. Okay.
Yes, sir.
Because I think that's what actually happened. But they lied. They said it's if more than 3 people. So let me just go here. Okay. Matsudiso, I will send you the link. I'll try and send you the new link by email, and I'll have to send
Yes.
them the new link as well. Rats. This is that's actually what happened. Sorry, it took me a while to figure that out. I'll have to send them a new link, and